Yeah, and then we can
adjust it.
We can adjust it. So either we do this one on Thursday, and I've got room to deliver a lecture on Friday afternoon, giving the students some opportunity to study, or we'll just keep the timetable as it is.
Yes, we can.
Did you say? I need to see the map. I think maybe we're Ludhiana. So was that where you wanted to Here this yes? Good to record? Okay. So thank you very much for being here on the Monday morning for the second week of our GIAN course on miniaturized total analysis system. I hope you all had a great long weekend. I particularly enjoyed playing Holy on Friday. It was really good fun working with the dice as well as the water balloon. So I think it's a great celebration for someone that had never done it before. As I thought that today it would be good to start off with a little bit of a recap, trying to think what we actually achieved last week. Because as mainly a chemistry, agricultural science focused audience, we've seen a lot of energy. We started off at miniaturization of chemical analysis systems, where the main driver was to increase efficiency with added advantages, including the decreased consumption of samples and reagents, as well as the decreased consumption of power, because we don't need to pump as many liquids around in our chemical analysis, which reduces the need for electrical power. Another great advantage of miniaturization is that everything gets smaller, which means that you can package it all up into a small box that you can either in a small suitcase or even using a handheld device can carry in the fields to do your testing close to the site of where the chemistry is taking place that you're interested to probe. The last advantage of having miniaturizing the analytical systems down to the point that you can bring it to the field is that you cut out a lot of time. You don't need to transport your sample from a river to the laboratory because all the processing is automated. You don't need to do a whole range of sample preparation. So typically you get your answer about your chemistry within an hour. For small molecules, typically we can do 10 to 20 minutes, but if you have DNA, you need to have amplification. An hour is a reasonable time to get a result. Microfluidics, I've introduced you to the difference of the physics happening when we are at a sub-millimeter scale. And microfluidics is nothing more than a toolbox that enables the miniaturization of these chemical analysis systems. So we have ways that we can do the chemical analysis, the chemical assay itself smaller, but coincidentally the microfluidic timescale, the sub-millimeter, the microfluidic scale, the sub-millimeter also is the same size as that cells are growing in our bodies. So cell and systems biology can also be conducted using microfluidic system. And lastly, for those of you that are interested in the fabrication of either in or the fabrication of particles, microreactors are you can do organic synthesis and the formation of nanoparticles in systems as well. Over the weekend, as I had nothing better to do yesterday, I rearranged the lecture from Friday from applications in DNA and protein separations to have it more focused on ways of making nanomaterials and having some agricultural science applications. So it's still an applications-focused lecture, but in this instance a little bit more focused on the interest of the people that are in the audience. So our toolbox has a whole range of different functions. They are up to transport and meter samples and reagents, including external pumps, such as syringe pumps or pneumatically driven systems, or intrinsic pumps using either wicking, the wetting of the capillary, and therefore pulling the liquids in, or using the electroosmotic flow. Because we have low Reynolds number, mixing becomes a challenge, and we looked at a couple of different ways that we can faster mix the chemical reagents. We looked at different ways of separating, so we had touched on HPLC, high performance liquid chromatography, which we will study in more detail this week, and we had an intense day on electromigration techniques for separation using either capillary electrophoresis to do the separations where we had some broadening but could achieve really high resolution. And we had separation of molecules by isotechophoresis, where we may be sacrificing a little bit on resolution, but we could concentrate the molecules from a dilute solution, could concentrate them into a very small volume, and therefore at a high concentration. And million-fold concentration factors have been demonstrated with isotachophoresis. After this separation, or a selective assay, which could be a coulometric reaction, it could be electrochemical detection, or it could be an immunochemistry or aptamer-based interaction for binding, like's done at the lateral flow assays and the COVID tests. We can detect the presence of our analyte, and that detection could be quantitative. Yes, it was there. No, it wasn't there, but we're not sure how much. Or it could be qualitative or quantitative, where we also can measure how much of our analyte is present. Good morning. Using calibration curves. So today and tomorrow we'll be focusing at a different aspect, and that is how can we actually make these devices. So we looked at why do we want to use them, where do we want to use them, what are the functionalities that we have, and for the coming 2 days we're going to look how are we able to put it all together. And the way we do that is by microfabrication. We pretty much borrow all of the technologies from the electronics industry. So microfabrication is best described as the foundation technology and platform for creating microsystems. It provides permanent fixed microstructures and assemblies that can allow us to conduct a wide range of functions and applications. I still have got the old slide change on. So microfabrication technologies, we all have phones in our hands. They are all made in clean rooms using microfabrication processes. Wearable sensors are increasingly around, with phones measuring or watches measuring our heart rate, measuring how many steps we put every day. Chemical analysis, but also medical test devices get smaller and smaller. Again, measuring your physical parameters like your weight or your heart rate, as well as the chemical contamination. Do you have a certain virus or not? And then we've got applications for organ on a chip. We'll be looking at in more detail on, I think, Thursday. We'll have a lecture on how microstructures can be used to culture cells, organs, spheroids and organoids, to build a little near human system where we can test the pharmacology, the acting of drugs, and the risks associated with that. Microfabrication is mostly done in a clean room facility. And a clean room is an engineered space where there is a very, very low concentration of particulates. It is well insulated, well controlled from external factors, and actively dust and particles are always being removed. So a clean room is typically at a higher pressure than its environment. So dust and air are pushed out continuously, and the input air is filtered through a series of different filters to prevent any dust from being introduced. We'll be talking a little bit later about photolithography, the way that the microchips are made. But we use a lot of light-sensitive materials, which means that big areas of a clean room are yellow light, so that we can easily work with our materials. We don't get unintended cross-linking happening. But you can also see in this picture that everybody is dressed up to prevent the presence of a human from contaminating the environment that you're in. One of the practicalities is that if you're dressed like this and you want to ask a colleague a question, you need to know who it is. This is the only part of the face of your colleague behind safety glasses you can see. So you need to get to know your colleagues really well to put the right name to appeal. Because in a clean room, other than body height, everybody looks exactly the same. Everybody is dressed up in the same way, wearing overshoes, gowns, trousers, gloves, having a hood on, and in some instances also a mask to prevent any dust coming out or just skin cells dropping off. So it is a little bit of a challenge to recognize people, but at a certain point you start figuring out eyes and eyebrows. We have different classes of clean room systems, and and these classes are given on how many particles are present per cubic meter. For example, class 100 clean room has got 100 particles per cubic meter. A class 10 only has got 10, and that is the kind of clean rooms that you really need to make mobile phones. For microfluidics, we're actually quite happy with the 10,000. 10,000 particles per cubic meter is still very, very little. It is a lot cleaner than our normal laboratories that we work in. And a lot of our cheaper microfabrication that I'll be talking about later, that is okay for microfluidics, actually doesn't need a clean room at all. We're going to have a little bit of closer look on how are these devices actually made. What are the processes that we have borrowed from the MEMS industry to make these microfabricated devices. And the particular ones that we'll be going through today, in the first lecture, we'll be looking at photolithography as the basis for the standard silicon processing in the clean room. The next lecture this morning will be going towards soft lithography, which is using templates made using silicon machining or other ways, but then to cast a relatively soft polymer called PDMS on. And then this afternoon we'll be looking at injection molding and other replication techniques. And tomorrow we'll be focusing on the use of 3D printing. Professor Malik and I have been fighting for 4 days, I think, no, nearly a week. We started on Wednesday with DHL to get all the certification right, because I forgot to pack my little box with show and tell pieces. Yesterday we won the battle with DHL and we've got all the documentation that I, as a foreigner, can receive a parcel at the chemistry department whilst I'm staying on campus in a hostel. It was a very interesting challenge that I had addressed it to the chemistry department. DHL started talking to the chemistry department. People don't live there, so we needed to get a letter from the hostel. It's been all kinds of interesting numbers of paperwork, and I'm not sure if that was all necessary, but I hope by today the box will come, otherwise it's tomorrow, and it's got some show and tell pieces. The important part to realize in microfabrication, there is often not really a right and wrong. It depends on your situation, as well as the application that you've got in mind. And the approach that you pick is typically a combination of what kind of chemistry you want to do, which dictates the material that you can, but more importantly, the materials that you can't use. If you want to use a good solvent for polymer, you probably don't want to make a polymer device, you probably want to make a glass device. Whereas if you want to use hydrofluoric acid, which etches glass, you probably don't want to pick glass as a material. You're probably a lot better off with a Teflon device. Cost is your budget, and do you want to have one device or disposable, that drives how many devices you want to, what the price per device is going to be. Because if it's going to be disposable, you probably don't want your manufacturing cost to be much beyond 500 rupees. If it's a device that you're going to be using over and over again, maybe 5,000 is not a bad price. And it also very practically depends on the facilities that you've got on site. If you've got a beautiful laser cutter sitting in the School of Engineering, that may be a very convenient way for you to do rapid prototyping. Whereas if they have a high resolution 3D printing, then you could make exactly the same structures using high resolution 3D printing. So the facilities that you've got quick access to are an important driver as well, which very much varies from institution to institution, and explains why standardization is a great problem in microfluidics. Everybody just makes with what they've got available. So our application dictates a lot of the different areas of what we want to do. We already talked about chemical compatibility, but the analytical assay that you want to do, that's a whole range of demands onto the microfabrication approach to choose as well. If you want to do optical detection, or you want to look at something under the microscope, transparency is going to be very important. If you want to measure the conductivity or the impedance, you probably want to have a conducting material. And we also need to be able to interface with the electronics on the outside. For separation, if we want to do liquid chromatography, we probably need to have a material that can very tightly be bonded to enclose the microchannel, because otherwise our device will pop open during operation. We want to make sure that our looking at functional integration, how can we integrate a filter for sample preparation, for detection, or a transparent window where we can do optical detection. So integrating the different steps of the analytical workflow, each of the steps put a different demand onto the material properties that we want to get into the device. Then we have the consideration, is it going to be disposable or single use? If we want to have a reusable device, then, or we're just doing rapid prototyping to get the design right, then direct fabrication techniques are fine. But if we want to have a disposable like the COVID tests, we probably want to consider high throughput replication techniques like injection molding, because otherwise the cost is just going to be unaffordable. If we need to pay a salary for someone to make every single device, it is never going to be available for 50 or 100 rupees. So we need to then replicate it using very similar technologies to the way that we make plastic drink bottles. And the commercial potential is also important to understand where you sit in your path towards commercialization. Are you a PhD student that thinks that you can make nanomaterials using a microfluidic device, and you want to test 3 or 4 different mixers? At that point, scalability of your manufacturing is not really critical. You just want to try if the design works. Whereas if you've got a full assay developed and you've got a commercial partner interested, at that point, the scalability of your manufacturing approach, and if your design can actually be made by injection molding, where you can make thousands of devices for 52 or 100 rupees each, is going to be really attractive. So where you sit in the technology readiness levels, between I'm just a PhD student trying out some designs to I have my proof of concept, I've demonstrated this all works, I've got an investor, I now want to get to market, that dictates where your choice of fabrication approach as well. So during this lecture we'll start off with photolithography. And photolithography started a little bit with the history of photography, where you can see that the projection of images using lenses initially revolutionized the drawings. So here we can see, and I think it was Yusuf that did this as well, but you can see that a picture of a tree on the street could be projected onto a sheet of paper and then be traced by hand. So you could make a drawing a lot easier, relying on fewer artistic skills than just looking out of the window at the tree. Oh no, that's the camera, so that was Da Vinci, that was the camera obscura. Then Nice comes here. So this in here, we can see a man sitting with the behind his desk, and this is the very first photograph where light hit a light-sensitive substrate and changed the chemical properties wherever the light hit, and didn't and the darkness shades into a photo. And that happened somewhere in 1826, 1827. So 2,000 years ago, no, 200 years ago, people started making photographs. With a material, which is the powdered butymate, was suspended in lavender oil. This was spread in a very thin layer on a base, and the base could be either a metal plate or a glass plate, and then it was being dried. I don't necessarily am after the history, but a lot of this processing is actually the same thing as the photolithography that we use these. Clean rooms are fancy things, but the processing, it's not rocket science. It's very much this. So once the thin film was being deposited onto the glass, it needed to be left for a little bit, preferably heated, to remove the lavender oil, to remove the solvent. And then there was a coating left. That would then be exposed to the light. So the camera obscura projected the light of the image of the tree outside, probably upside down onto this plate. And after that exposure, nothing was visible yet. But some of the material where the light had been hit had been cross-linked, and some of the material where the light hadn't hit hadn't cross-linked, which meant that chemically the bitumen of Judea, the material that was present in a very thin layer, had at some locations changed its chemistry and at other locations not. And that change in chemistry was facilitated by light. After even do the development anymore, because we just use our mobile phone. So we started off with a camera obscura. Then NIPS discovered the fact that we had light-sensitive materials that we could change the chemical properties of by exposing some areas to light, not others. So the Kodak film camera came in around 1860. Then there was the Polaroid camera, where where at a party you can quickly click a photo and the print comes out directly. From 1975, the digital camera has found a way into its lives. That became digital SLR cameras. The first cameras were on the phones in around 2000, and right now, everybody has got the most beautiful high-resolution camera sitting on their phone, and we're snapping pictures everywhere where we go. But the process underpinning microfabrication and the processes transferring the designs onto the thin film on the wafer is exactly the same way as the NIEPs use the camera obscura to transfer the image of a scene in the lab or a tree outside onto their light-sensitive material. We still use light projection to transfer a geometric pattern from a photo mask to the light-sensitive material that we call a photoresist, that is deposited into a thin film on our substrate. And then we may not always use this thin film directly, but here we can see that the pattern is being transferred from the mask onto the substrate. We can see the pattern's photosensitive layer after development. Some areas are left there, some areas have been removed, which means that we now can selectively etch or remove parts that are not protected by our photo light sensitive material anymore, and not others. So we can do some etching and selectively remove materials. The selective removal of the parts of the photoresist allow us for that etching, and the photoresist itself, it is mainly temporarily. Some parts where we talk about soft lithography, we may use the photoresist as our template, but quite typically our photo patterning is only there to do our subtractive micromachining afterwards. So we chemically etch materials away and we use our photoresist to protect. Once we've done our etching step, we dissolve our light-sensitive layer, we dissolve our photoresist, and we are left with selectively etched grooves and reservoirs. In photolithography, very much like the traditional process developed 200 years ago, we need to first dispense and deposit our light-sensitive material. And we do that with a machine that we call a spin coater. A spin coater is almost like a CD player. It's just the wafer is held by a vacuum chuck. It rapidly rotates around, which means that a gravitational force spreads the liquid into a very fine film, where the rate at which we speed becomes a measure for how thick the film is going to be. The faster you spin, the thinner the film becomes. Then we get the exposure to UV light, which typically happens in a mask aligner. So that's where the light exposure takes place. And then we develop where we, depending on the tone of the photoresist, we either remove the exposed areas or we remove the underexposed areas. So there's two tones, two types of photoresist. One, the UV light breaks bonds to make the exposed areas soluble. The other one that I just already talked about, the light photo crosslinks, it polymerizes and makes it insoluble. In most applications, the wafer needs to be cleaned before the photoresist is being put on. So you may want to, if you have a silicon wafer, first remove the surface bound water, then use some HDMS to create a hydrophobic surface so that we get even wetting, and then cool back down to room temperature before depositing the photoresist. So you place the wafer. Yeah.
Go to the back slide, please. We use only HMDS. That's the only material, or there?
HDMS is it is a siliconizing agent where if you've got a silicon wafer, it can add, I think it is C18, it can add a carbon functionality, which makes the surface very hydrophobic, which means that the oil-based photoresist wets a lot more evenly. So it is a chemical that reacts with the silicon on the silicon wafer and then adds a carbon tail to it to enhance its hydrophobicity and make sure that the surface chemistry is perfect to stick the photoresist to.
Is it the only material used?
No, there's a whole way of different photoresists will have different primers. So it's the most commonly used one.
Okay.
So the wafer is then placed on the vacuum chuck, the vacuum sucks it down, you dispense the photoresist, it accelerates, and then you wait till it is kind of dry to touch before moving it into an oven without getting prints on it. The photoresist itself, it is organic light-sensitive compounds that are present in a solvent. And we've got two different types. We've got a positive photoresist where the exposed regions become more soluble, and the positive masks, which means the exposed areas will be removed, so we'll create a dent wherever we've exposed the light. And then we've got negative photoresist where the exposed areas will harden, they will cross-link, and then a negative mask, the inverse of the picture, will be left after exposure. So here we can see with the same photo mask, with a negative photoresist, we'll be left with the exposed area as a positive feature, whereas with a positive resist, the exposed area is removed. Our resist remains where the light hasn't hit, and we create a little dent. So your mask may need to be mainly black or mainly transparent, depending on the tone of the photoresist that you decide to use. But the negative tones ones are most commonly used for microfluidics. So after the photoresist is applied to the desired thickness, there is initially a quick soft bake at a lower temperature to drive out the solvents, after which it's cooled down to room temperature, and so that it is not tacky anymore. Then we go to the mask aligner. For a single exposure, alignment is not very important, and you could just do it with a flood exposure system. But if you make complex systems where you want to have different features overlapping each other, at that point it is very important that your second exposure aligns with the features that are already on your device, and that's where the mask aligners come into play. And if you then think about the technologies used to make a phone, they are often 20-step processes where they get back to the photolithography 20 times. So After exposure, the exposure, it's typically UV light. There's also deep UV and E-beams to get even finer resolution, but your bread and butter exposure source is UV light that travels through a light mask. The mask is black and white or black and transparent. The black blocks the light, the transparent allows it to go through, and we get our chemical reaction taking place between the resist and the light. And only the areas not protected by the mask will undergo the chemical reaction. Then we go to development, and each photoresist that you buy has got its own purpose developer to go with it. Some of them, typically the positive photoresist, they develop in basic solutions, so solutions that are pH 8 or 9, whereas your negative photoresist tend to be organic solvent like Pectia is one of them, but yep, so organic solvents are being more used for the negative resist. Remember, for the positive resist, it is the exposed resist that is dissolved while the unexposed remains on the wafer, whereas for the negative resist, it is exactly the other way around. And you know if it is a positive or negative photoresist because it's written on the bottle. After we've done the exposure, we hard bake, and that means that we lock the material that we've got on our wafer in place. And the hard bake typically takes place at a higher temperature than our soft bake before. And you allow the wafer to cool down to room temperature again, so you can touch and handle it. Then there's an inspection step where the pattern needs to be accurately transferred to the right location. The line width of the pattern images need to be having the correct size, and we should make sure at this stage that there's no dust particles or defects, because it's not worth processing any further. If we're all happy after inspection under the microscope that our photolithography has gone well, then it's time to go for the etching. And that is my least favorite and at the same time really nice reagent. It is HF. HF is hydrofluoric acid.
Can you go a little slow?
Yeah, thank you. So the etching of the glass is done using hydrofluoric acid, which is a nasty chemical. If your application requires the use of glass, please check all your safety requirements if you want to do some wet etching of glass, or make sure you are in a facility where the use of hydrofluoric acid is allowed. One of the problems with hydrofluoric acid is that if it gets into your nail bed, it starts eating away your nerve system. So if you're working with HF and there would be an accidental spill and may have ended up on your hands, your nail needs to be removed, and there's a special balm to extract the HF again from your finger bed. I've not had to use it, but I had a training where they told, so every clean room using HF etching has got nail removal kits. So if you can avoid making glass devices, do so. Otherwise, make sure you follow all the precautions, because it is a very nasty chemical to be working with. Hydrofluoric acid etches isotropically, which means that it etches at the same rate in all directions. That means that if we've got a hole in our mask for etching that has a certain width, then the etching will go as much in the width as it does go into the depth. And that means that your channels always get a lot wider at the top than they are at the bottom. So here you can see we etch probably 20 micron deep, but that also means that our final feature is 20 plus 20 is 40 micron wider than originally intended. So we need to take that into account in our design phase, because we can't have our channels 20 micron apart if they become 40 micron wider during the chemical processing.
How it is occurring? Why they are getting...
Because the etching process, it works at the same rate in all directions. So it's isotropic, which means that the HF doesn't know if it's going down or left. So at any point where the etching starts, the etching rate is the same in all directions. So we etch as quickly to the bottom as we do etch to the sides. There are some ion bombardment etching techniques as well, which are non-isotropic, which only etch in a straight line. So if you think about sandblasting, with sandblasting you have a straight beam of particles, and only the particles that are hit will be removed. So that is anisotropic, you've got a clear direction. Whereas the HF etching, because it's the chemical process, it goes the same in all different directions, which means that you get under etching and your channel ends up wider. So you get under etching and your features always end up wider than your design. There are alternatives to etching glass. There is powder blasting, where with a very fine powder you can etch away, physically remove parts of the glass. And then the photoresist, because it's a polymer, it's bouncy enough to work as an etch mask as well. And then increase work in high power lasers to do three-dimensional patterning and structuring of glass to break it, and then it can be dissolved out. The bonding of the glass, you can get a perfect bond, but you need to have a furnace, and you need to, for about overnight, so 12-14 hours, thermocycle, go up to 650, 660 degrees, back to 600 to relieve the stresses and allow the glass to thermally fuse together, because you've got one part of your wafer that you've got etched your grooves in. You then need to put another flat wafer on top in order to create an enclosed microchannel. So you need a furnace for that. So glass is great because it's chemically inert, it's transparent, it's electroinsulating, it is strong, it doesn't deform under pressure, and it's a surface that chemists is very well known to chemists. Most chemistry developed in the laboratories has been done in reagent tubes, round bottom flasks, Erlenmeyers. Chemists are used to glassware. They know how their reactions behave on glass. So that makes it very intuitive to do our chemistry in microfabricated devices, also in glass. The problem is that glass is expensive when you compare it to plastics. I just told you it's risky processing, it needs special facilities. So processing glass is expensive. It's a direct manufacturing approach, which means that you need to have a pair of hands, even though the clean rooms have some robots around. But every device needs to go through the whole manufacturing flow, from depositing the photoresist all the way to the etching and the bonding all over again. So there's no replication options. It uses hazardous chemicals. HF itself, it's nasty. Thermal bonding, there's a little bit of luck involved to get a high success rate. And glass is fragile. If you drop a glass device on the floor, it may break, whereas with a polymer device, it won't. So that's the first part of today. So we talked about photolithography and glass etching. We'll take a little break now. Let's keep our fingers crossed there's tea. That seems to be a little bit random. Some days there is, sometimes there isn't. Then I'll be talking about soft lithography, which is using PDMS, very popular technique in the laboratory. And then this afternoon we'll continue on injection molding. If there's any questions, please ask, and I hope that sometime today we'll get some glass devices, but Professor Baga, he had a couple of glass devices with him, so that gives you a little bit of an idea how they look like. Thank you for listening, and let's see if there's a cup of tea.
Quickly, if I want to go through all the steps
Yeah.
for making that, you went very hurriedly. I could see the things. First part that you were saying, coating on the wafer was done.
Yeah.
So can you repeat those in a minute?
So first you need to make sure you've got your light sensitive material on. So you pour it on or have a One really nice website, if you want to look up anything else, is Make Simple Microfluidic Devices. And they go through a lot of detail on how PDMS micro devices, but also paper microfluidics that we'll be playing around with later this week. It provides really easy to understand instructions. With our tea will come in 15 minutes or so. So we'll make a head start to make sure that we don't get called out with lunch.
Okay. I want to take water in a bottle full.
Hi. So this is a good website where it gives prices, where you can source different materials to do both PDMS. You should be able to get a copy. You should get a copy of the slides with the course. I've given copies, so all the slides should be available at some point.
They'll be giving at the end.
Okay.
I just want to go through few of the things after
Now.
the day gets over, so I would just note down the things and then try to go through.
So soft lithography is the use of the mask that or the silicon wafer. We've done our photolithography, we've got bits of our photoresist left, and we've got other areas where our photoresist has been removed. If this was a negative tone photoresist, this would have been the need to get it right now. Negative photoresist, crosslinks. So this would been exposed. This would have been a non-exposed area. What happens is that you then pour a two mixture polymerization that I'll give the details of later. It's a highly viscous liquid. You pour that over the substrate, allow it to cure in the oven, and it's a flexible polymer, so it then can be peeled off. And one of the nice things is that it actually is flexible, so it can move around a little bit. This slide here very much clarifies the topic that we just were talking with. Where does the design come from? And the design of the device that you're going to make sits in the photomask. And the photomask, you could make a very simple drawing in a package like PowerPoint, but mostly you'd use CAD-based software to design your file, and then a photo mask can be made either using a commercial printer, or if you've got a very good print facility at your university, a high quality laser printer may also already do the job.
Kindly go slow.
So the photo mask, as you can see here, it's made to go through the transparent areas where it will expose those areas of the photoresist, which after the development, the exposed photoresist is better cross-linked and therefore will remain on the substrate. Material is washed away. So we have our full plate here coated with photoresist. We only expose a cross structure, two crossing lines with little circles to be able to make easy reservoirs. We only expose those areas. They will cross-link. During the development process, all the other photoresist washes away, and we're left with these structures sitting on top of our wafers. And if the package comes in from DHL today, I have a couple of wafers there, and you can actually, with your finger, you can just feel the structures sitting on there. What we then do is that we cast the pre-polymer mixture over it. We can peel the polymer off and then stick it to another flat substrate where the ridge that was present on this template will end up being a little groove in our PDMS because it's cast over it. If we seal that to a flat substrate, we've got a microchannel left. Sign.
Okay.
I've got the structure here. So this is the structure. So it is the same material they use to insulate electronics.
Yeah.
It is also the same material they use for silicone implants. It is the same material you use for siliconing in the bathroom. So it is the squashy material for caulking in the bathrooms, that's silicone as well. So it is that squashy polymer material. The one that works really well for microfluidics is called Silgard 184, sold by Dow Corning. The whole world is using it. They must have a right pre-polymer length or something. So you buy Silgard 184. There's a whole range of different places where you can buy them. You mix it in a 1:10 ratio, pour it over your template, and then you can peel it off after you've cured it for about an hour at 80 degrees, or you can also do it 2 hours at 60 degrees. There's a range of different processes.
1:10 ratio of what? One is this.
So you take 10 parts of the base polymer, 1 part of the of the catalyst.
Okay.
And the whole process should be playing on this movie. Did I put it there yesterday? And yesterday it played. Let's see if it wants to play. There we go.
Today we're going to show you how to make a PDMS microfluidic device. PDMS is a cross-linked polymer that is poured over a mold to make channels, microfluidic channels, in your device. This is an example of a final PDMS chip. Mold that was used to make this chip. You can make molds out of a variety of different materials, as I mentioned later. You can also 3D print your mold.
So a mold is
Or you
anything
can use a combination of materials,
positive structure on there that you can
such as
cast.
this one, which is a push button device, which is made from cut sheets and side.
Alright, to get started
Very
with making our
simple. That's how I
PDMS-based
show it.
device, we're going to take a weight boat, put it on the scale. With the weight boat on, we're going to tear, or you can press 0. Basically, we want to weigh out the appropriate amount of elastomer or PDMS based on the weight. And so the ratio that we want to use is a 10-to-1 ratio. So I'm going to start off pouring the base, the PDMS base. I'll pour 30 grams. PDMS base is a very viscous liquid. So you can see it's going to come out kind of more with the consistency of honey. And then as the numbers go up, I'm going to kind of watch it as it gets close to 30 grams. A little bit more. Oop, now we're going to go a little high. But then what I'm going to do to kind of keep my mess contained, you can see I'm twisting
It is
the
very
bottle.
sticky. It's very painful to
And I
clean
got
up.
a little bit of PDMS on the lip that I'll then just wipe off with a chem wipe and dispose of that in the regular trash. Okay, so I was a little bit high on the amount, but like being a little bit off is okay. So the next one I'm going to do is tear, and then I'm
It doesn't play in presentation mode. There we go.
Today we're going to show you how to make a PDMS microfluidic device. PDMS is a cross-linked polymer that is poured over a mold to make channels, microfluidic channels, in your device. This is an example of
That's where we got to.
here. In comparison to the base, the PDMS base, the curing agent is less viscous, so it's more the consistency of water. So instead of pouring, I'm actually going to use a transfer pipette, and we want to measure out 3 grams.
So 1:10 ratio, about 30 of one, about 3 of the other.
Again, so
No, this is the
so
catalyst. So
little bit
there
less
were
than
the 2 bottles.
next amount.
So this is the second reagent.
Yeah.
Alright, so a little bit high, but again, that's okay. You're not exactly at 30 and 3. Alright, so then the next step, I'm going to take, we've got our PDMS base and curing agent. So I'm going to take this off the balance and then rigorously mix.
And mix.
Alright, now we're going to mix somewhat rigorously, but also for at least a minute or two. Basically, the goal is to make sure that these two components are mixed very well, otherwise we'll have problems later in our manufacturing.
It's very viscous, so mixing is hard.
Alright. That looks pretty well mixed, so we can stop our mixing. When you're picking up your spatula so you don't drip everywhere, I recommend kind of spinning it around and holding it over a hem wipe on your way, or some kind of disposable items on your way to the trash can. Alright, now that we've mixed these two components together, you can see there's a lot of bubbles that form during the mixing process. So what we're going to do next is put this into a vacuum chamber and use that suction to help pop and get rid of all of these bubbles. Here's the vacuum chamber we'll be using to degas our PDMS today. So you can see I put an aluminum foil lining. This is just to contain any mess in case your PDMS spills.
You only clean up PDMS once, and then you're very careful keeping your lab clean because it sticks to everything.
Chamber, close the lid, and then we already have our vacuum turned on. So just make sure you find the right tubing. So you can turn the vacuums on, find the right tubing, and connect it to your vacuum chamber. And then at this part, we're going to turn the valve such that we're pulling vacuum from only the chamber. Let this set for about 10 to 15 minutes until the bubbles are gone. Alright, so the next step before we pour our degas is to actually prepare something to pour it into. So for this type of master mold, which is has a laser cut double-sided tape to form our channel features, I'm going to actually put a piece of aluminum foil that I've molded into the shape of a petri dish within the dish. Make sure there are no tears in the foil around the creases, and also that the foil is about as flat as you can make it in the center of the dish. To minimize leaks, also minimize PDMS that might run under your master mold. If you're concerned about a non-level surface, you can also tape your mold to the foil, which I won't do this time, but that is an option in later fabrication.
The aluminium foil makes the getting device out later easier.
The foil. So next we're going to pour our degas PDMS on top. Alright, so in order to remove our degas PDMS, I will not just take things apart because that will cause the PDMS to splash. First what I'll do is I'll actually turn off the vacuum. So that's off. And then the next step, I'm going to close the valve so that way the in between the chamber and the outside is closed off. So now I've changed the valve and then I remove the tubing. And then next what I'll do, go and take off this red cap. That's optional. We can also evacuate through the other hole. And I'll very slowly turn this knob to allow air back into our vacuum chamber.
If you do it too fast, it becomes a mess and it's cleaning up again. So it's all minimizing your cleaning up work.
Okay, so once it's fully evacuated, you should be able to easily lift off the top of the lid. Alright, so now you can see there's still a few air bubbles within the mixture, but this is an acceptable amount. Compared to before we put this in the vacuum chamber, there was a lot of air bubbles, so we successfully degassed our PDMS.
If it wouldn't be acceptable, just put it on the vacuum for another 20 minutes.
Degas our PDMS, we'll take our boat and then our liquid boat and pour it into the features. Since we degas it in a separate container from our master, to try to avoid introducing air bubbles, we'll pour slowly and also close to the surface. And I like to just pour over the center of my master mold. Then as an added tip, if you want to get more of the PDMS out of your boat, you can actually take one of these spatulas and scoop it out, depending how thick you want your final PDMS device to be.
If you've done some cooking with honey, it is very similar.
And then last but not least, we'll just put this in the oven between 55 to 65 degrees Celsius for about 2 hours. If you have a 3D printed mold, check the temperature limits of that 3D printed plastic because you may have to use a lower temperature.
If you need to decrease your temperature,
Next,
you need to go for
we're going
longer.
to show you how to use plasma to bond this PDMS, already complete PDMS chip to a glass slide. And we'll do that by first cleaning the PDMS and the glass, baking the glass for about 5 minutes at 100 degrees Celsius, and then applying a plasma treatment for 60 seconds, bonding the two pieces together and putting them in a 90 degrees Celsius oven.
There, because we haven't touched on bonding yet here, but that I think gives a nice visual of how simple it is to make PDMS devices once you've got a template. So PDMS as a material is really good because it has a Young's modulus of 1 megapascal, should have been a capital P there, whereas most polymers are a lot harder. They are about 1 gigapascal. So PDMS, it's really squishy. If you know the caulking in your bathroom, the squishy material that you put around the sink to prevent water from ending behind your wall, it is that level of squishiness. And again, I hope that the devices come in today so you can actually have a feel of them. It confirms over a large area, and so-called hard PDMS, so PDMS where you, instead of using the 10:1 ratio, you've used a little bit more of the cross-linker compared to the polymer base. It becomes a little bit stiffer, but it then becomes really good at replicating nanometer-sized features. It is transparent, also in UV, so compared to some other plastic materials. If you want to use some UV fluorescence, PDMS is still great. It's chemically inert, so there's a lot of solvents that it is compatible with. It's got a very low surface energy, and you can bind it reversibly to most flat substrates, PMMA, COC, glass, silicon. You just take it off your mold, stick it on, and you've got a water. That activates the surface and allows you to irreversibly stick your PDMS to glass, and that means that you can apply a lot higher pressure before the device tears away from the substrate again. It's a durable material, can be easily cleaned and reused. It's got very low thermal expansion, so if you want to do PCR, it doesn't shrink or expand a lot when you're doing thermocycling. It's biocompatible. It is used sometimes as a food additive. It's used in food packaging. It is used in implants. So it is safe to use, and it's also environmentally benign. So you can just the waste, you can just put it in the bin. And after fabrication, because it's so flexible, you can just peel it off the substrate, and it can replicate nanometer size features. So here you can see a substrate was made using nanolithography, and you can see that the small features, submicron features, are very nicely related into the PDMS structure, which again becomes important if you want to grow cells on a chip, because sometimes cells like to have a micro or nano structured surface. Cells don't really like something flat. You can use the replication ability of PDMS in order to create these devices. Then a little bit more detail about where the lady was going into the movie. How do we bond PDMS? PDMS chemically, it's a polymer, but it is close to glass. And if we put it under a plasma, we can, for the loss of water, we can chemically bind PDMS to either another slab of PDMS, or we can use, as the other side, we can use glass. And that way we get a chemical covalent bond being formed between our microfluidic structure and the cover plate, which means that we get very strong bonding. So it is understood chemistry. We can activate the surface using a plasma. It removes the organics, it activates the surfaces, and then we get a chemical bond being formed. What the plasma treatment also does is that it changes the contact angle. So native PDMS is hydrophobic, so water will bead up. But if you treat it with a plasma, if you activate those oxides into hydroxide groups by opening them up, we can actually get a lot more hydrophilic substrate with a very low contact angle. The challenge for the use of the devices, however, is that we have what you call hydrophobic recovery, which means that the polymer chains, they rearrange and we get back from our hydroxylated surface to having our silicone material again, which is hydrophobic. So over a few hours, we are back with the hydrophobicity where we started, unless we chemically covalently link. In this case, HEMA was grafted to the hydroxide groups. At that point, the hydrophobic recovery is not as effective, and we can continue to work with a hydrophilic substrate. This may change due to the hydrophobic recovery, and that could be problematic.
When you want to test off.
Okay. I think after this one is a good point. So, if we do droplet microfluidics, we have a continuous phase is typically the solvent that is wetting our microfluidic device, and the dispersed phase, the one that's making the droplets, is the one that is not like the chip material. So if we've got a hydrophobic chip, then our continuous phase will be the oil and our droplets will be aqueous. If we've got a hydrophilic device, then our continuous phase will be the water and our droplets will be the oil phase. If we have a PDMS droplet system with hydrophobic recovery, we may see a phase inversion where water and oil swap who is continuous and who is dispersed phase as the surface chemistry changes. So from that perspective, doing only a plasma treatment and not covalently changing the surface chemistry is a dangerous thing to do for droplet microfluidics, because you may change the identity of your dispersed and your continuous phase. At the same time, the hydrophobic discovery comes with a change in surface charge. We've learned from Professor Baga, surface charge is the driver of electroosmotic flow, which means that during the hydrophobic recovery process, our EOF will be unreliable. Our EOF will slow down and slow down and slow down because our density of anionic charge on the surface decreases. Again, something to keep in mind, oxygen treatment is really good to get the bonding. If you want to use your devices but want to have stable surface charge, you may just put them on the shelf for 2 days till the hydrophobic recovery is complete. Or you may want to surface modify your PDMS so that you're not reliant anymore on the surface charge. I'll be talking about different ways that we can use the flexibility, the air permeability, and the qualities of PDMS as a sorbent in more detail. But we've got tea now, so let's take a little break and then we go have a cup of tea, and then we'll continue on the journey. Do detection of the light intensity through, all of a sudden your intensity changes just because your channel has ballooned out. If you're doing detection, you're working with Beer-Lambert's law, and your measured signal, your absorption, depends on the path length. If you inflate your channel, you increase your path length, and your calibration curve that you had developed is no longer applicable. So it is important, if you work with PDMS and you apply pressures, that you realize that it may change the size of your channel because the material can inflate. So if we have the channel, we can change the surface properties. We can also use that change of properties to mimic biological processes. I've already spoken about organ-on-a-chip devices, and they mimic organs or little organoids by culturing human cells in microfluidic devices. To get the environment as biorealistic as possible, it is important to realize that not everything is stationary in our body. If we think about our heart, it is pulsing. Our lungs are expanding and decreasing in size. Our bowels are having peristaltic movement. None of these systems are stationary. So if we want the cells to behave like they would be in our body, we need to have a way to also mimic this movement. Again, PDMS is a very suitable material to do this because it's got its flexibility. So like we can inflate a membrane here, we can also have pneumatic control layers here in the side chambers. If we apply a vacuum, we can stretch. If we get back to normal, we can push it back together. If we do that in pulse rhythm, we can actually make peristalsis in the bowel or the breathing movement, and the cells continuously have to adjust themselves to being on a stretching and recompressing substrate. Again, flexibility of PDMS is one of the few materials you can do this in, because a lot of other plastics will break if you try to do this. So having this soft material provides great advantages. In my own research, we've used this to simulate traumatic brain injury. So traumatic brain injury is if you hit your head twice after one another. Typically our head can deal with one blow to the head. You can hit your head once, and if nothing else happens, you may have a headache for a few days and your brain will heal. But if your head, in that recovery period, if you hit your head again, your neurons in your brain may actually die and you may end up with a permanent disability. And traumatic brain injury is a major source of disability in people under 45. One of the reasons this system is vulnerable is that neurons are not quite a normal cell. If you think about a cell, you think about a kind of a near spherical ball where there is a nucleus and mitochondria and everything around. But you think about something that's kind of compact. Neurons are the only cell that are not. Neurons have an axon. So they've got this very long arm that your neuron sits in your brain, and this very long arm goes all the way through your spine and electrically and chemically interacts with other environments in your body. Because these axons travel to different territories, it makes them actually really vulnerable to damage and disease. And indeed, there's a lot of diseases of the brain where neurodegeneration, the killing of neurons in the brain, is the cause of the illness of the patient. One of the nice things that can be done with microfluidics is that you can make devices that you can study the neuron and the axon separately. The cell body, the big part of the neuron, is about 20 micrometers, whereas the axon is 1 or 2, so it's much, much smaller. Moving this way. What that means is if we see the population in a PDMS device, we've got a PDMS device here with 100 micron deep chambers for seeding our neurons, but 5 micrometer grooves connecting to another chamber. When we seed a neuron population into this chamber, the cell bodies will all stay located in this chamber because a 20 micron cell doesn't fit through a 5 micron hole. The axons, however, only need 1 or 2 micron to go from one place to another. And they're curious, so they like to explore their environment. So a couple of days after you've seeded neurons in one of these culture chambers, the axons will actually expand through the grooves to the other side, which means that we've got an area where there's axons only. Combining this knowledge that had been started off by the Taylor group, combining this knowledge with the idea that we can balloon the PDMS, made us wonder if we could actually put a little balloon under these axons to mimic a stretch injury on a neuron. We thought that if the neurons would be sitting on the surface and we balloon the surface out, it should create a short pulse where the axon is being stretched. So we apply the pressure. Here the neuron is just the way it's cultured. Here all of a sudden the neuron gets stretched. So we made a device. So we bought the device from a company that makes them that had the small channels for the axon. So here we've got the somal side. Now looking from the side. So we had the top view in the previous slide. We now look from the side. So we've got the deep chamber where we can see the neurons. Leave them for a few days and the axons will find themselves away through the 5 micrometer groove because they're all smaller than a micron themselves. So you don't need to do anything. They like finding nooks and crevices because that's the way that they find their way through our spinal cords as well. We then put a PDMS base with a microchannel covered with a membrane under there so that we could inflate the substrate to stretch the axons, just like a little balloon. The setup, if you go to the original paper by the Quake group, they actually provide you with all the hardware as well as the programs how to control the quake valves. So there's a couple of different solenoid valves. There's little connectors to connect to your fluidics, and there's a little board you can create to connect it to your computer, that you can say, for the first 5 minutes I want these 3 channels activated, I then want those others. So both the software and all the components you need to buy are available online from the reference with the paper that I just showed. Using this, we used an optical profiler to measure how much we could deflect our surface by inflating the balloon. And here you can say if we increased from about 12 psi to 40, we could deflect our membrane from 2 to 5 micron. Relatively small, but should be biologically relevant to the way that an axon actually gets stretched in the brain when you're in a traffic accident. So we hope that we would have a model here for inflicting traumatic brain injury to a neuron. And indeed, here we've got a control. You can see the very thin line of the axons growing. After 5 hours, you can still see the lines. After 24 hours, the lines are still there. If we apply a 35 psi pulse, which means that we deflect, we inflate our balloon to 5 micron high and then down again for 7 seconds, which is kind of the bang that you get to your head and you get your concussion. You can see that after 5 hours, you can see some blebs being formed in these axons. And after 24 hours, you can see that these get more and more pronounced, and actually they don't connect anymore. So the axons have completely beaded up. So a 5 micron injury, 4.5 micron deflection for 7 seconds is enough to kill the axons. If we look at that with fluorescent stains, you can see the beading up a lot more clearly. You can see without the injury, the axons are nice and smooth. After the injury, you can see all these blobs being formed, which is agglomeration of protein at one place, which means we'll get a shortage of protein at other places. And that means that the axon is on its way to die. If we look at the soma side, so the soma is the cell body. Remember, we had the big 20 micron blurb that contained the nucleus and the mitochondria, and then the thin axon. This is looking at the axon. This is looking at the cell bodies. Here you can see the cell body itself with the nucleus. If we have no control, we can see a healthy growth where we've got the dendrites and we get very little blebbing. Whereas if we can see after the injury, even at the soma, we can see the blebbing taking place, which means that despite the fact that the injury took place 500 microns away from that body, which is a very long distance for a cell, the signaling of something is wrong actually progresses all the way back to the cell itself. And all the cells here in this injured, after the injury, are unhealthy. And if we repeated this injury twice, so this is here injury and it could kind of recover. So this is the time that when you have a blow to your head, you've got a headache for a few days and you may not be able to read. If you get another hit, so if we had inflated our valve, left the devices for 24 hours, then did another pulse, they all died. And that is the problem with the repeat injury, and why after you've hit your head significantly once, you need to be careful for a couple of days, because within a certain window, your neurons lose the ability to recover if you get a second blow to the head. So this here is an example demonstrating both that using microfluidics, we're on the same size scale as cells. So we can use microfluidic features to separate our cell bodies and our axons, and that way conduct complex biological experiments to look at a cell-based response. And that is something that you can't do when you're culturing your cells in a petri dish. So microfluidics provides us with new opportunities to study biology. At the same time, it also showcases the benefits of PDMS. PDMS is flexible, which means that using a small pressure pulse, we can deform surfaces, we can create these stretch injuries. Adding a tool to our toolbox, studying how cells respond to something like a stretch injury. So that's all using the flexibility of PDMS. The next part of PDMS is that it's air permeable. For cell culture, that is very good as well, because cells respirate. They use oxygen and they release CO2. So having an air permeable material to culture your cells in is actually really, really good, because that means that new oxygen can enter the device and the used CO2 can leave the device without us as people in the lab needing to do anything. The material is permeable enough that there is a continuous exchange of gases from our microfluidic environment with the incubator that they're sitting in. This air permeability of PDMS can also be used for gas sensing. Here we've got a very simple microfluidic channel structure where we can pump gases through, a thin PDMS membrane that gases can permeate, and then a gold electrode where we can measure SPR resonance spectra because the gaseous molecules move through the PDMS film, contact the gold and change the resonance of the material. Another example of where the air permeability of PDMS is used is in making an artificial lung. All that our lungs do is they oxygenate the blood. They allow us to add fresh oxygen to our bloodstream, exchanging the oxygen for the CO2 produced by respiration in our bodies. Here we've got a device that contains a PDMS membrane to do exactly that same functionality of air exchange, making a kind of an artificial lung, or I think this was an artificial placenta, but both of them allow for the gas exchange. What they've done is have the material packaged in Teflon, which is not air permeable. So the outsides are not air permeable. And then inside the device, there is a thin PDMS membrane. When we have our channels with our blood being alternated with channels with air, the gas and CO2 will exchange, and that will allow us to remove the CO2 from the blood and add the oxygen. And here you can see that the engineers made a nice structure to maximize the surface area, just like the bronchi in the lungs maximize the surface area for exchange. Here, this doormat-like structure is used to increase the surface area to ensure our PDMS film can aid in the exchange of water and CO2 between air and the blood. If you're interested, I've given the reference here. So, air permeability of the PDMS is really good. Another neat way of using the air permeability of PDMS is that actually all the air that is in PDMS, if you put it in the desiccator, you can suck it out. And that means that you've got kind of almost a sponge willing to suck up more air again. And you can use that to fill microchannels even if they don't have another end. So here, if we've got a micro device in PDMS that has been put under vacuum in the desiccator, all the air has been vacated out of the PDMS. When you add a droplet of liquid, it will actually be sucked into the device because the PDMS is drawing the air that's present in the microchannel into the cavities in the PDMS, which is at a nanoporous scale, nanoporous materials. All those cavities that have been sucked empty under the vacuum are really keen to be expanded and filled again. And we can use that as a way to pump liquids, even if it is a channel that's got a dead end. Because the air that was occupying the space in this microchannel is being sucked up like a sponge into the PDMS. We can just fill our channels by having a small piece of PDMS only put in the vacuum chamber and seal that on top of a microchannel. This little bit of material will act as a little vacuum pump and allow you, without the need for any pumps, to move your liquid through the microchannel. So it will add as a little permeable. This last example here is where we've got a sealed microchannel with outlets and a thin PDMS membrane. If we apply a vacuum to the other side of the membrane, the air will be pulled through the membrane and our liquid will fill the channel. The nanoporosity of the PDMS, however, does not allow the liquid to go through. So we can remove the air bubbles from the PDMS, we can introduce liquids without the fact that we get air pockets being filled there. One of the ways that this vacuum sealed PDMS has been, or this vacuum treated PDMS has been used, is to sense a number of different biomarkers in blood. One of the big challenges when you're doing chemical analysis on of blood is all the blood cells. You've got the white blood cells and the red blood cells, and if you want to do detection. So we prefer to remove the blood cells, and the cell-free blood is called plasma. Here we've got a microfluidic plasma extraction chamber, which is a little bit deeper and allows for the extraction of the plasma cells, as that will be shown on the next slide. The cells will stay behind here, and then the vacuum will pull the plasma across a sensor for the biomarker detection, all driven by PDMS strips here that are suction chamber. They are bits of PDMS where the air has been evacuated out from under using a vacuum source. So here we've got the microfluidic device. We put it under vacuum for the PDMS. So, and if we then put the blood on there, the air that was present in the device absorbs into the PDMS, allowing our liquid to fill the vacancies created. Here we have a very simple step structure that, due to the forces, the cells will try to fill the cavity here and move to the bottom of the reservoir. It means that a cell-free mixture will stay on top. So the particles experience a force when they go from into an expansion area. We've seen the expansion arrays before with the particle movements, and this is a use here for the separation of particles from the fluids. The particles move into the expansion, allowing us to collect a particle-free liquid here at the other end. And the particle-free liquid is an engineering term. In biology, we say that we separate the cells away from the blood and we collect plasma. So here we use a fluidic phenomena imposing a force on the particles to go down. All the blood cells sit in this waste reservoir. We start off with blood, we end up with plasma. The plasma passes our electrochemical sensors, and we are able to detect our biomarkers in an environment free of cells. This device didn't need any active pumps or anything. All it needed was to be placed under vacuum to vacate all the air from the PDMS structure, and then the PDMS itself could drive the fluidic transport. All really beautiful parts and properties of PDMS. However, on Thursday, before we went on the long weekend, we had Professor Malik talking about SPME, solid phase microextraction. Does anyone realize or remember what the material was that these SPME fibers are made of? It's on the slide. PDMS. The same PDMS we've been talking about for the past hour. So as an analytical chemist, I get a little bit scared about using PDMS devices. If in liquid chromatography and gas chromatography, we use it as an ideal sorbent because our analytes really like binding it, would this really be the best material to do chemical assays in?
Yes, yes, yes.
So there is does have limitations. You can use it for extracting, but if you don't want anything to extract, you can't stop it extracting molecules from your sample. There's a couple of people that have looked at that. Here we've got fluorescent images of Nile red that was introduced into a microchannel repeatedly. So introduced, taken out, reintroduced. And you can see every time it happens, the fluorescent intensity goes up. Because more of our Nile red, our hydrophobic small molecule dye, actually is extracted into your chip material. Here you can see that if you pump it through your channel, you get your channel and your walls become increasingly fluorescent. I particularly love this image where the liquid has been taken out of the microchannel, and then they took a razor blade and chopped it through half. This is our microchannel. Our analyte has actually gone into the walls. Would be nice if we would be doing chromatography, maybe. But if you want to be separating your analytes here in your microchannel, it is no good if your analytes are sitting all around. So for cell culture, you can pacify the surfaces. You're typically talking with proteins that are not that prone. But if you're doing small molecule testing, please note that PDMS is a sorbent. If it works good for solid phase extraction, you need to carefully pick your analytes and make sure they're hydrophilic. Because if you work with PDMS and you develop an analytical assay for a slightly hydrophobic molecule, it will, like the Nile red has done here, enter your chip material, which means that your detector is not going to see it at the end of your assay. Worst, if you use your chip for 2 or 3 days, your baseline will go up and you're not doing your assay anymore. You're just measuring the amount of analyte that's building up in your device materials. So that's one of the things that is important to realize. Here there is, they've done similar experiments with quinine at different pHs. And you can see that if you fill your microchannel at low pH, you can wash it away. But if you go to higher pH, you actually will be able to start staining your channel, playing with the pKa of the quinine. If it's hydrophobic, if it's protonated, it will move into the PDMS. If it is deprotonated, if it's neutral, so if it's charged, it will stay in your channel. If it's neutral, it will go into your device. So make sure you think what your analytes are doing. And I think, so I thought this was in the next lecture, but I think we have time. Yeah, we have plenty of time before lunch. So if we look at the problems of PDMS as a sorbent, there is an alternative on the market which is called Flexidyne, which doesn't have as much of the sorptive properties as the PDMS. And it is also very easy to work with. So it is a polymer film that you buy pre-made. You can replicate it by simply pushing something in it. So it's not necessarily cast. It is already polymerized when you buy it. You can use a simple hole puncher. You also use to make holes in your belt to create inlet. And you can then seal it, stick it to a substrate. And then I hope that this movie plays, because that shows how the devices are being made using the Fluidyne. Oh, there we go. That's the previous slides. Try my previous trick, because I could very nicely, when I went out of the slideshow mode, it did play. Can we make it big? data has run out. So like the movie with PDMS, this quickly shows how easy it is to make the device with the fluidine. So the material itself, I don't know the price by heart, but it isn't a cheap material, but it saves you from having to buy a significant infrastructure. There we go. Move the speaker your way again. And I'll see if I can. Hello? So you can see you buy it as a film. That is the polymer. That's the PDMS that we've seen earlier today. We know how messy a desiccator can do it if it overflows. Let's see if it wants to go again. Because it previously didn't. Ah, now we are. We've woken up. So that's where we were. It's just a thick polymer you can easily process. Imprint your structures on there and then reversibly seal it to a glass slide. So that's just PDMS is very widely used, but it is not necessarily only material you can fabricate in. There are alternatives coming in onto the market. Flexidime is one of them. There's a few more. So if you are afraid of PDMS and what it could do with your analyte, there are always options to do something else. And now the movie wants to keep on playing. So for making devices with PDMS, it is a really fantastic material, particularly for cell culture. It is gas permeable, which means that you don't need to continuously oxygenate your media that you're pumping in, because respiration takes place through the walls of your fluidic device. It is flexible, which means that we can use it for pumps and valves. So the valving we've shown with the quake valve, where we had a little balloon that we can inflate. If we put a couple of them in series, we actually have a little built-in peristaltic pump that we can control by having a pressure line and some solenoid valves controlled with a not too hard bit of software. It is optically transparent down into the UV. So if we want to look at cells and do some staining with it, and then look at fluorescence microscopy, we can also use your blue dye, so the DAPI dyes, which expands the number of different fluorescent dyes we can use. Biologists tend to want to look at 4 or 5 proteins at a time and make fluorescent images of them based on the different labels. So the broader the range of light is that we can have our fluorophores, the more molecules that a biologist can see by staining the cells. On the other hand, a transparent microfluidic device is really convenient to work with, because you can inspect it under the microscope, you can study your processes, you can see what's going on. So transparency is important. PDMS is also electrically insulating, which means that we can do electrophoretic separations in it. It is chemically inert, so it's compatible with a lot of solvents, which is good if you want to do some organic synthesis. And once you've got a template, and there's a vast variety of different ways that you can make templates, you require very little infrastructure. It needs a bit of time, and you need to make sure you don't work too messy, because cleaning up is a lot of work. But it does allow you, if you've got a balance and an oven that can heat up to 60-65 degrees, you are in a position to make PDMS devices. And most laboratories out in the world have the facility to have access to an oven and a balance. So you can, it is a democratic technique, as in once you've got a template, you can actually replicate the devices quite easily. Gas permeability, great for cells, but if your solvent, if you want to do a long-term assay, and slowly but certainly you're doing something in 50% ethanol water, and your ethanol slowly evaporates off out in nowhere, your 50% solution is no longer a 50% solution. So you may be losing volatiles from your sample, from your buffer, if you keep them in your channel for too long. Gas exchange is great, but you need to understand your material properties to know if the PDMS is the right choice for you or not. At the same time, and I think Professor Malik will be talking about that with the HPLC, you typically want to degas your buffers, because you don't want to have bubbles in there, you don't have a lot of absorption of CO2, because it could be changing your pH. Our respiration is not one-way traffic. We don't only lose things out of our device, we also have molecules from the air entering our device. So we may get a slow increase in pH, because the CO2 from the environment slowly makes it into our buffer, forming a carbonate buffer. So you need to be understanding that gas permeability may be a problem, and you may actually not have the liquid into your device anymore, as you started off with. It also means that degassing for the purpose of just removing bubbles may not be very effective for very long. Yes, of course, you had removed all the gases from your buffer before you put it in. But by the time you've left your buffer for an hour in your device, you may see the nucleation of little bubbles again, because gases have permeated through the PDMS and entered your buffer, and may be able, if there's a little sharp edge on a corner, nucleate and form a small bubble again. And again, if you want to do anything, either metering or using electrofluidics, any bubble is an electrical resistor and means the end of your assay. You have to start again. So bubbles are not good in microfluidics, and the gas permeability provides a risk that you get more bubbles. Flexibility is great if you want to use valving. If you want to do HPLC in a PDMS microchannel, the likelihood is that you've got your stationary phase sitting in the middle. If you apply pressure-driven flow, your PDMS device will balloon around your column, and your analytes are actually not passing through your stationary phase, but around it. So if you want to do pressure-driven flow at high pressures, PDMS is not going to be your friend, because it's working like a balloon. The non-specific absorption is a problem. And that's why, despite being really popular for people doing cell culture, the number of people for analytical assays using PDMS is decreasing. And if people are using it, it becomes a single-use material, because you never know, if you do 5 different analyses, 5 different samples, your molecules from your first injection may be coming back in your 5th. So PDMS, yes, if you want to make a lot of devices, that's okay, but I wouldn't use it for over and over again for analytical assays, because you never know when your analytes are going to be rediffusing back into your assay. PDMS is also a manual process. You've seen it. It's not easy to automate. So it's not, the closer you are to commercialization, the less favorable the use of PDMS becomes, which means that it is not commercially interesting. So really good to try something out cheap, brilliant for cell culture. Analytical chemistry depends a little bit. Some things work like mineral ions, environmental samples. PDMS is great. Small molecule pharmaceuticals, think about those quinine pictures. I'd consider a little bit what pH you're working with. Hydrophobic dyes, don't go for PDMS, because you're do solid phase extraction into your chip material before you can analyze, and you're asking for irrepeatable data. So again, like everything that I'm telling you for your during this course, it is a toolbox. They're horses for courses. Depending on the essay that you do, either go to glass. Glass is not going to be being a molecular sink for your analytes, or go to one of the thermoplastics that we'll be talking about more after lunch. So if you've got any questions about the good, the bad and the ugly about PDMS, please let me know. It's nice to play with, it's a nice tool in the toolbox, but don't make it bigger than it is, because it has some problems as well. And as analytical chemists, we know how great it is as a sorbent. So keep that in mind. Same bucket of PDMS. Thank you very much for your attention. And we'll be back after lunch.
Can you quote some applications where we are using this PDMS as of now? Some practical applications.
Organ on a chip. So we'll be talking on Thursday about how we can make organs and organoids. The vast, more than half of the field of miniature total analysis system is focusing on making
यूनिवर्सिटी के न्यूज़ में आता है ना क्या प्रोग्राम चल
नहीं
रहा है.
मैम अब तो खत्म का ही भेजेंगे.
ओके, वो स्टार्टिंग में भेजनी थी बस आपने.
हाँ जी.
आउट ऑफ इंडिया collabs and yeah ऐसे जैसे courses मतलब this I find it very good. This is a very good platform जहाँ से
ये तो
आप
स्कीम में
बजरा तो अलग है ना.
नहीं ज्ञान की.
ओके
तो इसमें हमने अप्लाई किया मैम उनके साथ. तो
नहीं we need to find a collaborating party ourselves.
हाँ
Okay.
एक्चुअली आपके उसमें वो आपके उसमें ना क्या कहते हैं एक ज्ञान कोऑर्डिनेटर होंगे. वो होने चाहिए. वो ज्ञान के लोकल कोऑर्डिनेटर में सबको कोऑर्डिनेट करना चाहिए पर करते नहीं हैं लोग.
मेरे को तो ये भी नहीं पता वहाँ पे कोई है ज्ञान को कोऑर्डिनेट करने के लिए कि नहीं.
नहीं है तो आप उनको कह दो किसी को.
वो सर वही प्रॉब्लम है ना, कोई चार्ज तो नहीं लेना चाहता आजकल.
आप बन जाओ.
I will try to if I will get a chance.
So Malik, for the tutorial tomorrow, do we stay here? So that will be with the paper and the crayons.
Yeah.
I have crayons in my room,
Okay.
but the hot plates last year were in the chemistry building. Do we bring hot plates here or do we go to the hot plates?
Kindly let us know as well what material we want to bring, we should bring for tomorrow's activity.
I think we can just provide. So
At what time it is?
after the lecture, after the first lecture, so I will talk about from 9 to 10. Now from 10 to 11, I will talk about the theory of fluidics, and then we have hands-on.
We can go there, which is better.
I think it is easier to go there.
Yes. Just we take some photographs and upload them.
That would be better option rather than bringing hot plates here and
I think it will be dangerous in
Yes.
here to have carpet. I think it's better to be to
rather
may have nice rooms here to do drawing, but I think we need
Better we go there.
I think so. Yeah.
11 to 10 to 11 and 11 to
Lunch. So
we go there.
it takes longer than an hour. It may not take the full 2 hours, particularly because we are a smaller group.
Yeah, we go there.
So we then will need some food dyes if we have some colored liquids if you have them. If not, we can just do it with water.
I can bring whatever we want if you want me to get.
So what we will do is make very simple fluidic structures on filter
you want
with some crayons.
Okay,
And I already got the crayons.
Okay, you want some food colors as well?
If we have some food colors, it's nicer to see what the fluids are doing. It just makes it more fun.
Okay.
So liquid food coloring is
So that can be only one color, only one food color.
more is better.
More is better.
2 or 3, because then you can see.
One we
Flows
can
go
use
next to each
turmeric. One we can use turmeric as well.
Does that dissolve or is
Yeah,
it
yeah.
powder?
It can give the yellow color and water. We
Yes,
want the yellow
so-
color.
We want the yellow color, but preferably in solution and not suspension. Because otherwise the
We can
paper may
use the
filter the
super
particles
knitting.
out.
We
Yeah.
can use the super knitting.
Yeah.
Other can be the rice color. I think and the orange one is there only. And one more color you need to ask. Two to three colors now.
So two would be enough. So if it's easy to get to 2 colors, then we'll do that. Or we do 2 colors and no color. Also gives fun.
Yeah, we will get.
And you have some filter paper, maybe different Whatman.
Different Whatman numbers?
Just if we want to experiment and compare what's best. Because that's the cheapest and fastest way to make any device at all.
These kind of things help a better understanding.
It is really tiring to just be sitting in a lecture theatre over and over again and next information flow, so
it's difficult to be
be-
student again. I'm getting the feeling of a student.
yeah, it's a good point. Ooh, what's for dinner tonight? Ah, we're paying attention. It's hard to keep focus. I feel for you. Particularly doing second time around.
They are currently in the study mode only. So it's easy for them to focus.
I think it's always hard to focus.
Better than...
Yeah.
That's why I was trying to tell you, keep your pace low, let me absorb the things, whatever you are explaining.
Yeah.
If it is going
And that is
beyond-
good because
above your head,
if you lose
so-
it, they'll lose it as well.
Yeah.
And I've tried to pace myself having less information per lecture so that I do go slower. But quite often it just means I finish earlier. So I just need to have talk it through, think it through. It doesn't matter if you repeat something, because if it didn't
Yeah.
stick first time around, it may stick the second time.
Especially whenever you are explaining a process, step by process. So it's always better to conclude it, the steps in one go after the process is through.
Yeah.
So then all the things get recalled and reconnected in your mind. So then it gives a better picture of what the steps were. Should we start?
I was just looked at my clock and see if any more are here by past, and then we start. Because this morning, as soon as I started, they came in.
Yeah. I went out for water and I came back. Oh, another lecture started.
That was the mixed things up because tea was late.
Yeah.
We might be late for lunch.
It's part.
Yeah. The good thing about the recordings is that you can never really miss something because there will always be the option to revisit.
Yes. Especially when you are trying to learn something out of your domain. It's
Yeah.
always better to listen them.
And do some reading and then re-listen because
Yes.
it's the same thing like reading an article. Every time you do it,
Yeah.
you pick up something else.
Yes.
बच्चे ना मैं वो पहले तो हम जो कहते थे कर देते थे अब तो ना बहुत मनमर्जी करने लगे
पर ये सब हर जगह आ रही है।
अब लिया बेटा साथ और हमें कह देते कह देंगे
Are you good to get going? Are you okay to start the recordings?
We are ready, ma'am.
Okay. Because I've understood there's a program after this for me as well, so let's get the last lecture of today about the microfabrication by replication. Let's get that out of the way. So I hope you all enjoyed a nice lunch and be able to change your mind a little bit, because as we were talking, doing a whole list of lectures. How can I just stop the standard transitions? I need to look at that tonight. So it's always good to change your mind and be able to then refocus on the subject, because I realize I send a lot of information your way, and it becomes really hard to give it all a little bit of a place in your brain. So as a summary, this morning we started off talking about microfabrication, and then learned that photolithography is the heart of any microfabrication. How do you like my new laser pointer? It is a pointer, and it also a little flower and can do more. So if it gets really boring, I'll just put it up and you can watch that one. So we started off about photolithography, where we used a mask with opaque and transparent areas to selectively illuminate a photosensitive layer that we coated onto a flat substrate. Based on photochemistry, this interaction of the light with the light-sensitive material made this material change its properties, and then it became either soluble or insoluble in the developer solution, which means that we could selectively remove the exposed or non-exposed areas, and that way we could leave little tracks on the wafer in the photoresist that we could then either use as a template for soft lithography, or we could, when this photoresist was removed, use it as an etching mask for wet etching in glass. We built on that knowledge to talk about soft lithography, which is the casting of PDMS, an elastomer, over a template. And then PDMS is very good at replicating any surface features down to the nanometer scale. PDMS, you buy it as a 2-component mixture. You mix it in around a 1:10 ratio. The small bottle is a thermal catalyst that makes sure that the PDMS polymerizes when it's heated up. And typically you do the baking of the PDMS in the oven at a temperature anywhere between 55 degrees and 80 degrees. So you want to have it so hot that your cooking time is relatively short, about an hour or two. But you also want to prevent that any of your plastics that you use, either the Petri dish or maybe your template was 3D printed in a thermoplastic. So you want to prevent any of your materials from melting. You don't want any of your water that could be present to be boiling off. So you want to be at moderate temperature. But as anything in reaction kinetics, the warmer it is, the faster it goes. So you've got shorter cooking times or shorter times in the oven if you move up towards the 80 degrees. Whereas if for any reason you need to do your curing of PDMS at 55, you need to wait a little bit longer. So it's about an hour at 80 degrees, probably 3-4 hours when you do the cooking at 55 degrees. It's not very hard to identify that you didn't cook it long enough, because if you're making a cake, how do you know your cake isn't done yet? Fork. And what happens if the cake is not done?
So the liquid matter will stick to the fork and you'll come to know it's not good.
Exactly the same thing with PDMS. If the PDMS is not good, it's still sticky. It's still the sticky liquid.
Okay.
And you've seen all the precautions in the lab, using aluminium foil everywhere, knives nearby. It is very, very sticky, and there's no solvent that removes it. So you'll be there with a razor blade scraping it off the table if you do spill it. If it's not cured yet, you still have got your sticky goo that will literally stick to everything, to your gloves, to your door handles, to your tabletop, to your pen, to your balance. Everything will and it's sticky for weeks. So if you think it's still sticky, leave it for another hour. It is very hard to over-cure it, so it won't get dry like a cake. But you don't want your PDMS to be sticky, because then you'll have sticky stuff for weeks and weeks in your laboratory. What we'll be talking about during this lecture is mainly about injection molding, which is a large industrial scale process for making lots and lots of different devices. And these devices are made in plastics. And I'm not sure who's done any polymer chemistry here. Do you know the difference in plastic between a thermoset and a thermoplastic?
Thermoplastics can be remolded once heater, whereas thermosets cannot be.
Yeah. So if you heat a thermoset up, at a certain point it burns, but it will never melt and start dripping.
Yeah.
Whereas a thermoplastic, if you heat it up to around its softening point, it becomes flowy and fluid again. So that is exactly the property that we use to replicate our devices with high speed. So for injection molding, you want to use thermoplastics. And there's a couple of different ways of molding. Injection molding, as I just said, is the most frequently used techniques. But there's also hot embossing and compression molding. All three have in common that they use a thermoplastic. They heat a thermoplastic up to the temperature that it becomes a viscous liquid. That allows it to shape the liquid to the geometries that you want to replicate in a cavity. Then the temperature is dropped. If for a thermoplastic the temperature decreases, the plastic turns again from being in its liquid state to be in its solid state, and we have a solid device or a bit of plastic being formed. So in injection molding, the name is already much saying, you inject the thermoplastic into the mold. This means that we can get high throughput of hundreds is even conservative, thousands per mold you can make. And we have a number of, in my research group we recently purchased a 2-component injection molder where we have a PDMS base and a curing agent that are mixed together and then molded into the hot cavity to then do a very quick bake as we just spoke about the PDMS, and then the injection molder device comes out. So there is technology developing to do injection molding in 2-component mixture as well for then the thermoset polymers, but the vast majority is thermoplastics. Same thing for hot embossing, but the process works slightly different. We don't have the plastic heated up to the point that it's flowy, we just make it soft. And then we push a stamp like a cookie cutter into the soft material, we allow it to cool down, that it's solid, we remove the stamp, and we've got the structures stamped in. So in injection molding, we really are pumping liquid polymer into the cavities. With hot embossing, it comes to just above the softening point, and we squash a template into the soft polymer. And then there's compression molding where we've got a film and the film is shaped around the parts. Here we've got an image of the injection molder that I've got in my research group. So I've got a fantastic engineer in my group, Richard Alexander. A lot of the manufacturing parts here are all done by his hands. So he did an undergraduate and a PhD in mechanical engineering and has perfected how to engineer for manufacturing of microfluidics. And we are fairly unique at where we are, mostly research groups that have industrial instrumentation, but we've got a large scale injection molder. Like if we start at the start of the stage there, the injection molder would come to here. It is a large bit of equipment, like they used to make drink bottles, plastic cups. So what happens in the injection molder is that we've got a feeder hopper and you put a pelletized polymer in there. Could be any thermopolymer. The injection molder provides with control that you can adjust the temperatures, and therefore we can do PMMA, COC, that they are the main interest. Polystyrene, they're the main polymers that are of interest for microfluidics because those polymers are transparent. Not to as deep a UV line as PDMS, but certainly COC is coming with reasonable transparency at 380 nanometers and up. PMMA is a little bit higher. PMMA cuts out at around 450, 460 nanometers. So really the low 400 nanometer detection you can't do anymore. You need to go to the higher wavelengths. but the material comes in as little pellets, about half centimeter granular material. It sits in the hopper, it's getting a little bit of nitrogen being purged through to make sure it's dry and there's no water in there. Because if there's water and it gets heated up, it gets steam and all kinds of things. Then it's fed here into the screw. And this screw is rotated slowly so that the pellets are entering. And here you can see that there's heat, so this temperature moves up. So we get the screw mechanically, like industrial diggers work, where you can dig a core. The polymer is being moved forward through the rotation of this screw into a warmer and warmer environment, which means that it gets increasingly liquid. So we start off with pellets here. Here we probably have got a gooey mass, and here we've got a reasonably thin liquid. This liquid then, under the pressure of this screw that is pushing more and more material forward, the plastic comes out of a nozzle with high pressure and is injected, squirted into a cavity. We can see the cavity here has got some open spaces, and that is where we will be making our microfluidic devices in this instance. Works the same thing for phone covers, but we do microfluidics here. So this mold, you can see the arrows here, is sitting in place. We've got a small cavity. The screw pushes the polymer into the cavity. It fills, cools down. The cooled down part drops down into the supply basket after this platen is removed back anymore. So it comes back. This is all heated up to the melting point of the polymer. The liquid polymer is injected into the warm cavity where it stays a liquid and fills all the nooks and crannies. There's little holes there to vacate any air if that would be still present there. Then this is cooled down so that the polymer gets back to its solid state. The platen moves to the back. And here on the movie you can see how that takes place. So you can see the platen pushes the device away. Cavity closes. Liquid polymer is being injected. We then get cooling down. And then if the movie still plays, and comes out. Moves, part is being injected, comes out, and the pins push it out. So this is happening real time. So every 5 or so seconds, we have a new freshly baked chip falling into a basket. And that is presented. There's no other microfabrication techniques that go this fast. Problem, however, it is really expensive to make this part. So we can make many devices, thousands with one mold, but it costs tens of thousands of dollars. So multiply by 50, so $500,000 rupees or so to make the template to start making your first device. So injection molding is very attractive if you are ready to commercialize and you want to make 5,000, 10,000 different devices because you want to start selling them. Then it's not a problem to have high startup cost because your cost per device will be really low. If you're a PhD student with very little funding trying to do some microfabrication, injection molding is perhaps not what you want to do because you spend a lot of money making the mold and you'll only use 4 or 5 devices. So good for scaling, good for making lots of devices, depending on what your research project is. If you're relatively early in testing out the methodology, making an injection moldable device is probably not for you. So it's the top end, it's the Mercedes of large-scale manufacturing. Hot embossing is a little bit less expensive because the mold is not under as much pressure as the cavity and injection molding. You need to have very strong materials, high grade levels of stainless steel or aluminium being milled because your liquid polymer in injection molding is injected under high pressure. So you need to make sure that nothing moves or changes. Whereas hot embossing is a little bit more gentle. We start off with the template or the inverse of the structure that we want to have on the top, and we've got a polymer here on the bottom. We warm both of them up to the softening point of the polymer. So both the template is warm and the polymer is warm. We then push the template into the polymer, which is soft. So the polymer will deform where the ridges here are sticking out, and this polymer will displace. We then can cool down the mold, and the polymer with that cools down slowly as well, after which we can release the template, and we have our polymer device on one hand and our template on the other hand, and we can move again back to A, have our template, have a fresh bit of plastic, warm it up, imprint it, cool it down, and have the next one. Now that's why the techniques that we're now talking about are replication techniques. We go over and over again in the same loop, and with hot embossing we can make 50, 60, 80, if you're lucky 100 devices, so it's reasonable scale. It's a lot better than PDMS. If you use a photoresist template, somewhere between 10 and 15 bits start breaking off. So you can do a lot more with hot embossing than you can do with soft lithography, but is nowhere near at the side of throughput scale of injection molding. Compression molding sits kind of in the middle, but again we have a template here where we have a bit of polymer, so we load the polymer into our device. This is a moving part, this is a fixed part. With compression molding we apply more pressure than with injection molding. And you can see here that there's only a thin shim being left with compression molding, so you don't make large chunks of plastic. We then cool down again. This ejector pin can push the device out of the cavity once it's open again. Then we can load a new charge or a new bit of plastic, and the same thing happens again. So compression molding, very, very similar to hot embossing. There's also soft embossing, which is an approach where you use PDMS and not a hard mold to do hot embossing. So the hot embossing that I just showed was made with metal formed plates made using the Liga process, where you first do fine machining using photolithography. Then you electrochemically deposit a metal nickel on top, and that then becomes your hot embossing material to replicate your devices. So you're talking with a really strong metal mold. PDMS can be used as well if you control your processing parameters a little bit. So PDMS is a thermal insulator, so you need to heat it for a little bit longer. But it has been used very effectively to shape complex features into a thermoplastic. And after this has been pushed together, cooled down, the polymer is a solid again. The great advantage of PDMS is that you can easily peel it out because it deforms if you put pressure on it, which means that these complex, intricate structures are very easy to demold when you use soft embossing. If you use injection molding, you may need certain tapered sides in order to demold effectively, because you don't want to break off half your delicate microfluidic structure by removing your substrate. Here we've got a device where we first photolithographically pattern a resin, and then casting and curing that polymer, which then can be placed in contact with a PMMA plate. So we first use light and a mask to photolithography make a template. After development, curing, you can replicate this from a positive in a negative in PDMS, and then we can use that PDMS to put it in contact with a PMMA plate. You can then do kind of an in-house injection molding by using paper clamps to apply equal pressure across your device, put it in the oven to warm it up, demold, and you've got your PMMA device. So as you'll see throughout today, hot embossing, this is the standard process. It requires an expensive instrument. If you understand what the process does and you just need to get a polymer to flow to around the softening point to imprint a fluidic structure, you can actually do it using a low budget approach as well, and quite well. So here we can see some images on how these channels after hot embossing using the paperclip method actually works. So different exposure times here. Here we've got the original negative, then the PDMS replicate, which becomes the positive, and then PDMS positive is replicated into PMMA. So photolithography made in reverse into PDMS, then imprinted into PMMA. And you can see the structure is really nicely replicated from one feature to another. One is negative, the other one is positive. But we get very good replication of our features that were present after photolithography on our template, cast from a positive into a negative, and then replicated into a microchannel. So this is the way that the channels look like, and in this instance, it's nicely sealed. But if we think closely about the engineering challenges in injection molding, you've seen the movie coming in and out, and you can see that the device that is printed is released very easily from the mold. And that is because every part that you make by injection molding doesn't have vertical side walls. Because if it would have vertical side walls, it would be near impossible to slide it out of the mold again, because it would suck itself into place. So all the designs that we do, they don't have square sides as we tend to easily draw. They always need to have a draft angle, which is here to the side. One of the problems of a draft angle is that actually optical detection from the side becomes really difficult.
Can you repeat the draft angle?
So with the injection molding, we squeeze the material into a cavity, and we then want to be able to push it out again. If that goes with vertical walls, it requires a lot of force and it will be very difficult to get it out. Whereas if we have a small angle, then once we've got a little bit of movement, our whole device becomes loose and it's a lot easier to get out. Again, unlike cooking as an example, if you make a cake and you look at your molds to make a cake, it doesn't have right angles, it's got a little angle. And that is the draft angle, and that means that once you've made your cake and you want to get it out of the mold, the draft angle helps in that process. Microfabrication is just like making cakes. So same angle, same engineering concept, it's easier to get something out of that doesn't have perfectly straight walls. So for a research project where we wanted to do fluorescence detection coming from the sides, this draft angle, having a non-vertical side, actually becomes really difficult because you get it to work like a mirror. If your light shines to an angled surface, it will get reflected. So we developed a way that we could create a little detection window with a perfectly vertical side wall by making some changes to our mold. And what Richard figured out there is having a little insert that was part of the mold that had the draft angle, except for the little part that reflected the thickness of our microfluidic device. This element was put inside the injection mold, inside the mold, but then was spring loaded. So when we were pushing our device out of the machine, this could move along with the device, and then by the time it could pull out to the side, that would be happening. So this is in here, we have in the lab, we've got a CNC machine which mills really quickly with a spinning head, and we can go down to about 50 micron geometry. So we made this aluminium template by CNC milling, where this in here is the base, and this reservoir here is 50 micron high. So here 50 micron high features. And you can see some different reaction chambers because we wanted to do lysis DNA extraction amplification in these devices with fluorescent detection of the end product. So by having a special part in the mold that could leave the device earlier because it had the draft angles, except for the little height of our device, with the pushing out, this device could move along, but then as soon as our device, in the polymer device, fell out of the machine, the springs would pull it back in place, and once the plate is closed again, it was there to make the next device. And here you can see through the side of the device, you can see how very nicely the geometries of the microchannels where we could do sensitive fluorescence detection. A more recent project that I thought would be nice to get your head around again, what is all this microfluidic stuff good for? We are working together with Reza, and Reza is from Monash University, and Reza works on fertility, and in particular on in this project on how can we select the best swimming sperm. So he's developed a microfluidic device with a whole range of small microchannels, with the idea if sperm is motile, it will find a way to swim from one side of the microchannel to the other, whereas if it's not motile, it won't be able to find the entrance nor the exit. So in this device we load the semen to the outside. The good swimmers will be able to find themselves a way to the inside, whereas the not so confident swimmers will just stay outside and go to the waist. This means that you can select the best swimming sperm cells for in vitro fertilization from the central well. So Reza has developed this initially with soft lithography, and then made some changes to make it more complex using 3D printing. He's now got the problem or the luxury that he's working with the large in vitro fertilization aids, and he needs thousands of devices, which means that he can no longer make them by 3D printing because that's not as scalable financially. And we now need to translate the design made by 3D printing to make it good for injection molding, so we can make thousands of these devices for him, and we can start testing in human IVF clinics as well as for animal breeding. So there's a lot of interest in this kind of technology for cattle breeding as well. And horse breeding, there's a lot of money in that as well, clearly. So I've been talking a little bit between the lines about scalability and cost. And we recently wrote a book chapter where we actually did the numbers for a microfluidic device that by the time that you get your slides, you see a little bit bigger picture. Doesn't really show up well, but we've got a microfluidic device that's got microchannels on both sides. So both the bottom side and the top side have got some fluidics. We've got a sample inlet sitting here at the back that distributes our sample through different channels on the bottom. Then we've got some mixing happening with reagents when it's getting back. And then the sample there from the different channels ends up in the cuvettes, where the height of the cuvette is the detection path length for photometric detection. We looked at the cost per device that this would be in dollars, from $100 to $500, if we would make these devices by 3D printing or by injection molding. So 3D printing we'll be learning more about later this week. But there are, you can ask a printing company to print paper. There's also companies that will 3D print. So you send your design to the company, you wait 2 or 3 days, and then the box comes to your place with the 3D printing company. So they have the expensive machines, and they sell you for very reasonable cost. They sell you the prints. So we got this design into their calculator, and we calculated that the device like this would be around $125 to make. And it didn't matter if we made 10 1,000, 3,000 or 5,000, the cost per device was exactly the same. There is no benefit of scaling in 3D printing because the amount of labor per device is exactly the same. We can't increase the throughput. So we've got a flat line. But then with injection molding, I already said that the startup price is really high because we need to make the molds. But once we've got the mold, really our only cost is a couple of cents for the plastic. So you can see that the more devices you make, the cheaper injection molding becomes. And around 1,500 devices for this particular design is the break-even point where there is no difference between 3D printing and injection molding. So for this rather complex design, unless you need 1,500 devices, there is no need for injection molding. 3D printing will be as easy and convenient. And if you want to make some change to design, you're not locked in. If you want to go commercial, you want to go thousands of devices, by all means, injection molding will be your friend because the more you make, the cheaper it gets. Because this line will be continuing to be horizontal. This one will be getting closer and closer to a couple of cents. If we look a little bit closer at how the cost structure for injection molding works, we have the time that it takes to set up the machine and the method, and that will not be changing. That's a base cost. Then we've got the price to make a mold. For very few devices, that's a couple of $1,000. But there is a scaling factor where you want to go to a better quality mold so you can do more devices. So it becomes higher. And then we've got the materials cost and assembly. Materials scales linear assembly as well. So you can see there's a couple of points that all of a sudden you've got a step change in your manufacturing chain, and that is when the end of the lifetime of your mold comes. It's the same like your car. If you're driving your car, it normally costs kind of the standard money that you pay for insurance, plus the petrol that you use, but every now and then you need new tires. These are the points in time that you need new tires, and your car all of a sudden becomes more expensive to run, and then you forget about it, and then your tires are bald again. So that's the way that the cost develops for a manufacturing process of up to 5,000 devices with an aluminium mold. So when we're looking at thermoplastics, there's a advantage that there's a wide range available. Because one thing, COC, cyclic olefin copolymer, I think there's already 30 different grades in that one. So lots of different materials. We can combine materials. We can do something that's called overmolding. So we injection mold one material, and then we can add another material on top or around it. So we can do functional integration and combine different materials. Transparent materials are available, but COC is the only one that really goes deep UV. It is really cheap. We got a commercial sample of our COC, which was a bag about this high, and that was a free sample. People doing polymer processing really think large amounts, so 25 kilos is nothing. And it is compatible with high throughput manufacturing. The disadvantages is most polymers dissolve quite nicely in some organic solvents. So solvent compatibility may be problematic. Some are good, some are not, but it is always worth testing a corner of your device with the solvent you want to use to see if there's any, either it dissolves or it cracks. So solvent compatibility may be a problem. Thermal resilience may be a problem if you want to do PCR and you've got a thermoplastic that melts, where softening point is around 90 degrees. Maybe not great. If you want to do organic synthesis at 180, some of your thermoplastics would work. Ones that like COC is at around 220, that would be fine. PMMA is around 160, so you probably don't want to do PMMA. The surface chemistry is not as well known as glass. Chemists have worked for decades with glass, they know what's happening. Plastics have not been in the lab so long. Unless you're talking cell culture, because cell culture for years, decades has been done in polystyrene. So for cell culture, polystyrene would be fine. And the thermal conductivity of polymers is not as good as glass. So if you want to do fast thermal regulation, it will be still faster than in the bulk scale, but your thermal control in a quartz device would be a lot better than in a PMMA device. So these are all top-end technologies. The last 10 minutes or so of today, I'd like to show you that there's also different ways where you can make microfluidics just with something that you have available or you may be able to get from the hobby shop. We've got direct and indirect techniques where we can do micromilling. We then can do xerography, which is using a sharp laser blade to use an arm to cut little features out. There's 3D printing. There's also screen printing if you would like to make some functional electrodes. Having a space so you can get a conductive ink and make your microfluidic devices by screen printing. With xerography, again, you can make stencils in different materials. And if you want to make functional materials like electrodes, you can also use photolithography to lift off all the metal that you've deposited other than in the area where your electrodes are, and that way you can use electrodes like here for dielectrophoresis. So photolithography comes in a whole range of different price classes. We've got the expensive one where we've got a mask aligner that has a mercury lamp in there and a chromium mask. But we can also do photolithography using an LED array as a UV source and a printed overhead transparency as a mask. So here we've got a setup made in a laboratory that wasn't very wealthy, where they've got a UV LED, some focusing and collimating optics, an Arduino microcontroller. You're all not engineers, but if we think back about the 3D printing lecture, we had the single board computer coming by. So an Arduino is a board that is around $10 to buy, and you can do your old programming. It's a single board computer, and it can control your instruments. So that's not a pound, that should be a rupee. So the Arduino microcontroller is cheap and allows to switch on and off the lamp and maybe have some feedback control on the light intensity. With the transparency mask, you get here, this is a 200 micron scale bar. You can see that with a simple transparency mask, you can actually get really nice templates being made up. And here they could get down to a 5 micron via using a UV LED and a transparency mask. So you don't necessarily need to have access to a clean room with a mask aligner and all the bells and whistles. A UV LED with a transparency mask can get you to really microfluidically very nice features as well. Micromilling is another way that you can directly make devices by having a quickly rotating spindle that can remove polymer. Here we've got the tip of the instrument. It looks a little bit like a drill, but other than a drill, we've got a very fine tip, and this fine tip can write microfluidic channels where the quality of the surface finish depends on how quickly the spindle moves. So at 5,000 you can see a few bursts on the sides. If we get this spindle to go really fast at 20,000 RPM, you can see that this microchannel here has got nice surfaces. And it is about 2.5 lakh to be able to mill your own devices in polymer. Again, not as exorbitant as the cost of a clean room. Laser ablation is another approach that you can use to make microchannels, where you hit your substrate with a laser and then your substrate is placed, or your laser is moved on an XY stage, and by changing the position of the laser on your PMMA plate, you can write your structures with the laser in the plastic. At the point that the laser light hits the plastic, there's so much heat being generated that all the polymer vaporizes and goes into the air, leaving a microchannel behind. Typically, these microchannels are going to be 500 micron and higher. But we found in my research group that if you put a 10 or 20 micron pinhole in front of the laser, you can actually narrow down this beam and make 20 micron channels simply by adding a small pinhole to a hobby laser writer that people use to make little arts and crafts things and decorations for birthday cakes. So here you can see some of the channels that we make with the laser cutter, where this is what happens without pinhole. And if you go with the pinhole, you can say that with a 50 micron pinhole and a 35 micron pinhole, we could get narrower and shallower microchannels. So here we've got a very big groove with a lot of material deposited on the sides. If we use the pinhole here, right, remove still material from the laser, but not as deep and not as wide, and even smaller pinhole, exactly the same happens. So if the problem is that our laser beam is too wide, we don't have to go and sit and cry in a corner. We can actually narrow it down using a very simple optical part. Xerography we've already seen coming by with the lady explaining the PDMS replication. They were using xerography to make their templates to cast PDMS. The desktop cutters are again not horrendously expensive. We can go to around 300 micron channels with desktop setup. One of the nice things is that once you make something with a laser cutter, you can go at half intensity, you can make little lines so that you can fold your device from, like origami, from a two-dimensional into a three-dimensional construct, so you can have different fluidic layers. So here, let's see if we can get the movie working. This is an explanation on how fast the xerography actually works. That is focusing a little bit more on the drawing of the designs. So that's the cutter. As you see,
Hello
it's a
and
small
welcome.
desktop
In this
instrument.
video, we'll cover the rapid prototyping of a microfluidic chip with two thin films of PET plastic and an inner layer of double-sided adhesive tape. We'll start by defining our chip design. Here I'm using a stand-in with two inlets and outlets. You'll notice that there are two sketches here. They're both equal in size, the first of which we'll use to define our channel, the space in which fluid will flow through, and then the second one will define our inlets, our outlets, and the boundaries of our chip. I've mocked these up in Fusion 360, but you're free to use your favorite CAD package. This can be accomplished just as easily in COMSOL.
Or the free CAD package that we've
Our
seen
next
last
step will
week.
be to save these files, or to export these files as images. In Fusion 360, this is done with a drawing exchange or DXF file. I'll save the first one, defining our channel, and then do the same.
This goes a bit long, but it really shows you
For
everything
our
that you need
inlets and
doing, so
outlets.
it makes you also understand how quickly you can actually have a device.
Once we've done that, we can open the Cricut design space and start a new project. We'll click on Upload Image, and then in 2 steps, upload our channels and our through holes. Next, we can select these and insert them into our project space. There are several options at the top. One of the most important is the sizing. Here we'll define the width of the chip to be 1/2 inch, which scales to 1.5 inches lengthwise. Next, we'll select the channel here, click Attach to make sure that all of the cuts are done on top of each other, and then Make It. At this point, you can define where that chip is relative to the Cricut backing mat. Here I'll place it 8 inches along the x-axis and 1 inch along the y-axis before hitting continue. At this point, you'll connect your material, to the Cricut, and when making the cuts for the channels, we'll select vinyl. The goal here is to thinly score the double-sided tape so that it can be peeled off later. Now we'll load the material into the Cricut and press go. Here are those last few steps shown.
See how
in
fast
real
this
life.
goes, so stay focused. Done. So it's now with a very sharp blade cut out this structure.
Once the Cricut has finished making its cuts, we'll reconnect, click Finish, remove the first sketch from our workspace, and then upload the one with the through holes.
So they are your reservoirs that will
Define the
allow you
size,
later on to access
just
the
as
fluidics.
before, is 1/2 inch in width, and ensure that it's rotated appropriately. Select this, click Attach to make sure that all the cuts are made on top of one another, and then click Make It. Once again, here's what those steps look like in real life.
Done.
Once the Cricut has finished making its cuts, remove the material and the backing board from the machine. Turn the Cricut off, close the shell, and close out of the Cricut workspace before moving on to post-processing.
So that's important to make sure
The
there's no
first step
dust
in
in with your cutting
processing
blades.
is to remove the substrate from the backing. Your chip should then be able to pull apart really easily before moving on to the next step, where with a pair of tweezers or some other fine instrument, you'll carefully remove the tape lining the channel and punch out the inlet and outlet holes to your microfluidic chip. Then, adhesive side down, place your chip onto another PET film and press tightly to ensure a solid fit. As a quality control, here I applied about 10 microliters of blue dye to the chip, looking for any issues with seal or obstruction along the channel. This video is shown in real time, and as you can see, there was no evidence of either failure mode. This concludes this video of rapid prototyping of a microfluidic chip. Thank you.
So that shows that using a hobby laser cutter, a hobby cutter with a little blade, extractor machine, you can actually make microfluidic devices to try different designs yourself. And in this instance, they had one backing that wasn't, one where channels were removed from the middle, and one that contained the reservoirs to be able to get access to your channels. So very easy way of making the channels. I had planned to show this movie here during this lecture this morning. So this is the Fluidigm quick way of making the microfluidic devices. Two different things that I'd like you to get out of this afternoon's lecture. One is scalability is important. The more closely you get to a commercial product, the more likely your gold standard will be your injection molder. But if you're starting off in the field of microfluidics, it may be worthwhile to look around what the tools are available in your department, or perhaps in the engineering department, that you could make work for you. Don't forget about the creative arts. There's a lot of these cutting machines and laser ablation that are used in the creative arts to make earrings. I'm pretty sure the earrings that I'm wearing at the moment are made with a laser cutter. They've got a little bit of the print laminated on. The shape, I'm pretty sure this was done by a laser cutter. one of our administrative persons in our department has purchased a laser cutter because she's making the decorations that you put onto a cake with Happy Birthday, Professor Malik. If you want to make that custom, laser cutters are the way that it's done. Local business. Our admin person's got a little business like that. There may be one here in Patiala that offers cutting polymers for very other purposes that you could use for microfluidics to make some simple fluidic structures as well. Think about laser engraving, micro milling. One of the tools that is really popular is Dremels, what people use to make jewelry. That is all very similar scale to microfluidics. And there is xerography, which is the one that we just saw the movie about, where a very sharp blade can cut to a fixed depth to remove parts of a polymer film, and you can then stick different parts of polymer together to use it as a spacer to leave a microchannel in the middle. The review article that's given here provides a very nice overview of the wide range of budget microfabrication technologies that have been used for microfluidics. So yes, replication by injection molding is great, but you need a machine that is this big, and your materials only come as a commercial sample from 25 kilos upwards. That may not be the good starting point for a career in microfluidics. There are a lot of machines that are used for very different applications that can be effectively be deployed for microfluidics. So that was replication. Tomorrow we go over even cheaper, and tomorrow we'll be looking at how you can use and pattern paper to do microfluidics on. And the second session we'll be moving to the chemistry department, where we're doing some hands-on fabrication of paper devices. So thank you very much for your attention today, and I'm looking forward to seeing all of you again tomorrow.
separate किसी chemistry lab च central है chemistry lab कि जिन्हें ਆਪਾਂ मैं जिन्हें मैडम ने शेयर कर दी थी जिन्हें ਆਪਾਂ volatile जी करने otherwise you were saying SPM का बड़ा sensitive है कि तो नहीं लेना the only thing is when we want to quantify naturally quantify करना है